Hello students. So as we discussed in the previous chapter, moving charges and magnetism, when current flows through a conductor, it acquires magnetic property. What is that magnetic property? It can attract lighter materials of iron and it can produce magnetic field around it. Further in the discussion, we saw few particular type of arrangements like the wounded wire, which is called solenoid, which can actually produce magnetic field lines which are very similar to electric field lines for electric dipole. The discussion was detailed and we got to know about different laws, Biot-Savart law, Ampere-Circuital law, which can give us the clarity about the magnetic field lines produced or strength of magnetic field produced due to the current flowing through different kind of arrangements. So now, uh, in this chapter, okay, even in the previous, while even in the even while we were discussing the previous chapter, you might be thinking that, okay, fine. So, in order to produce magnetic field, the basic requirement is electric current. Without electric current, one cannot expect magnetic field to be produced. And but in our daily life, when I say magnet, it's not that the magnetic effect due to the current that I discussed which comes to mind. Instead, when I say magnet, it's about the hard stone like structure or material which comes to mind, isn't it? So those things which can actually help us or which can actually give us the magnetic effect in our daily life, like the magnets from the speakers that we from used or old speakers, what we get, the magnets or the experimental bar magnets, those things are actually come to mind. So now you might be thinking, okay, so what we have understood till now is, if we want magnetic field or if we want magnetic effect, we must first have electric current. But these are the hard substances, there is no current flowing through that. We are not making them any current flow through that, isn't it? We are not providing any potential difference. We have not yet owned any wire inside it. Even then, they can they can exhibit magnetic properties. They can attract, they can repel, but how is it happening? Isn't it? So, this question might rise in your head, and answer to all those questions, how magnetic fields or magnetic strength can be understood, or uh, the cause of it can be understood, the effect of that can be understood in this chapter. Okay, we will clear about all those things for the hard substance like magnetic field. So, the chapter that we are taking now is magnetism and matter. Okay. So, in the last chapter itself, we have actually discussed about magnetism, right? But this time, the discussion is about magnetism and matter. There it is moving charges and magnetism. A moving charge can produce magnetic field. What kind of magnetic field, how much strength it will have, all those things we have discussed. And in this chapter, since we have understood magnetic field, we'll try to uh, put that knowledge into the hard substance looking magnet and understand, analyze the cause and effect of the magnetic field or magnetic effect of that kind of magnets. Before we move any further, let us first see few interesting and simple experiments regarding with the use of uh, a magnet, okay, particularly a bar magnet. and then we shall move ahead. Okay, just a minute, let me show you a magnet first. So yeah, when I say magnet, magnets are of different shapes. See, this it has an history. Okay, it has a history. Somewhere in Greece, in an island called Magnesia, when shepherds went on for feeding their sheep, their their shoes with the iron hooks or iron nails, the shoes with iron nails, and their stick or what the rods with the iron uh, caps, they were stuck to ground and they could not move freely in certain parts, or when they move on top of certain uh, stone or rock. So that place is called Magnesia, and hence the magnet name comes from that. Okay, since the place name was Magnesia, we kept the name for this kind of attracting uh, property holded materials as magnets, and and hence the property as magnetism. So they are all natural magnets. Okay, the naturally occurring magnets. You directly hit a hammer on it, you can get somewhat like a stone kind of structure out of it. That random kind of stone structure is natural magnet, which you can directly get from the uh, nature. But these are all artificial magnets. We ourselves have given us this shape, and in many times we prepare the element or the substance which is required for this. We induce magnetic field into it. We do so many things with this. Okay, so these are all artificial magnets with specific shapes. And when we come to this artificial magnets, we have different kind of them. This kind of one, kind of cuboid shaped one, is called bar magnet. You know that. Along with this, we also have needle magnet, which very similar to a needle, which we make use of in actual compass for navigation purpose, and horseshoe magnets. Many other kind of magnets are available. Uh, but this one is called bar magnet. Okay, if we understand the properties of this bar magnet, we can apply the same knowledge to all the other different magnets. Okay, so before we move any further, say, the one with the white dot is north pole of the magnet, and this is the south pole of the magnet. Okay, so a magnet always has two poles, always has two poles. Okay, north pole and south pole. How do we decide them as north pole and south pole? When we suspend a magnet freely, the pole which directs us towards the north pole of the earth. Okay, geographical north pole of the earth is called north pole, and the other one is called south pole. Okay, which is directing towards the south. Okay, so it's not that first comes the magnet then the directions. No, first is always the directions. We call the upper part of in the geodical shape. You can observe the upper part is called North Pole and the bottom is called South Pole, right? That's how we classify them, North and South. North is to the top of us in the globe, and South is to the bottom. Okay, we knew the directions, but this aligned in that direction of north and south. So we named this pole which is directing towards north pole as north pole of the magnet, and this pole which is directing towards the south pole or geographic south pole of the earth is named as south pole of the magnet. Okay, so this is about bar magnet. Once we understand this bar magnet in detail, we can apply the same knowledge to all other magnets. Okay, so for now we'll see the few properties of this bar magnets experimentally, and let us come back for the theory part once we see those experiments. Hello students. So what you can see here is iron fillings. Iron fillings is nothing but pieces of iron, okay? Small pieces of iron, nothing else. You can see them. So here they are, right? I hope you can see them. Okay, so now these iron fillings, uh, once we put them onto any surface, they take, or any container, they take the shape of the container just like any fluid. Okay, just observe this. If I put these iron fillings into this, they get filled into that in that way, this way. So this is how the iron fillings look like. So, but here is a magic substance or material. Okay, what is this? You all know, it's a bar magnet it is, right? So this is the north pole of the magnet, this is the south pole of the magnet, right? I hope you are familiar with this. Now we all know that this magnet has attractive and directive property. What is attractive property? It can attract small pieces of iron, right? See, uh, see here I have an iron rod. So if I bring it closer, the iron rod gets attracted, right? So this magnet, the material which we have now, has the property of attraction. Obviously, it cannot attract all the materials. The materials should be ferromagnetic in nature. I hope you have studied three different types of materials: ferromagnetic, diamagnetic, and paramagnetic substances. So it can attract only ferromagnetic substances. This rubber, no, there is no attraction. Thread, no attraction. Paper, no attraction. But iron, yes, it can attract. So iron is actually a ferromagnetic substance. That's fine. They're all theory, but that's about attractive property. Then I've told you that it has one more property, directive property. So what is directive property? Directive property is the property of the magnet to align itself in a particular direction with response to the external magnetic field. See, now I have one more magnet with the thread support. Okay, see, this is the magnet that I have, and if I suspend this magnet freely, then look what happens. Okay, I've just, let me make it. Okay, so here is the magnet which is freely suspended in midair with the help of the thread. And you can observe that this magnet always comes to rest in north south direction. Okay, so this is the north south direction in which the magnet has come to rest. So this is the north direction and this is the south direction, right? You can check it. So even if I try to rotate it, say like this, in the, so this is east. Now if I try to align the magnet in east west direction, it won't. It oscillates for certain time, and after oscillations it comes to rest. Okay, see, I just want to reduce the time of oscillation, and after so many oscillations, as you can see, it has come to rest in north south direction again, right? See, yes, north south again. Okay, even if I try to bring it in south or east west direction, west east direction, it won't stay. Okay, so this is the directional property of the magnet. So now you are clear with two things. One is this material what I have here in my hand is called magnet, and this magnet has two properties. One, it has attractive property, the other, it has directive property. Attractive means it can attract iron and iron like substances, cobalt, nickel, and all. And directive, in response to the external magnetic field, it can align itself in a particular direction. Now, why does it align in north south direction? Because Earth's magnetic field is from south to north. Okay, that's the reason. Yeah, we'll get to know about them detailedly. But before I go for the next discussion, I would like to show you the magnetic field lines. Okay, yeah, because we have not yet seen magnetic field lines till today. Yes, we have discussed about it theoretically. Obviously, magnetic field lines are imaginary lines, but using these iron fillings, we can actually see magnetic field lines effect. Okay, look at this. The direction of alignment of these iron fillings gives us the magnetic field lines. Okay, I'm just pouring them randomly, but you can see while they fall down, they are taking a shape. Look at this, how beautiful it is. So, if you want to see that more clearly, let me shake it. Okay. Just keep observing how the iron fillings gets aligned themselves and what kind of shape can you see there. See, right, look at this. Yeah, look at this. Can you observe the magnetic field lines now? Yes, I hope you do. And these are present on top of it. Yes, and if I just want to clear them out, and now you can see them much better. Right. Yeah, now we have a perfect view of the magnetic field lines, right? Isn't it interesting? Okay, so now let us go and study about this magnet in detail theoretically. So, as you just saw, few interesting experiments there. Magnets are very interesting one, right? Okay, so moving ahead, let us put them everything in words now. So, what is a magnet now? Okay, see, we define magnet used based on its property. Okay, the exclusive or different property that magnet exhibit. when compared to the other materials. Using that, we define magnet. Okay, so magnet is a piece of material. Okay, it's a piece of material which has two major properties of magnet, which has attractive and directive properties. Okay, attractive and directive properties. So this is the definition of magnet that we can take. What are the materials or what are the substances which this magnet can attract? As I've just shown you it can attract. Okay, so the magnet can attract small pieces of iron, cobalt, nickel, etc. So now, yeah, I was telling you about types of magnets. One is naturally occurring magnet, natural magnet, which we directly take from the nature, directly from the ground. The other is this artificial magnet, which we give a proper shape, like a cuboid, it becomes bar magnet. You give horseshoe shape, it becomes horseshoe magnet. Give the shape of a needle, it becomes needle magnet, etc., etc. Those are artificial magnets. And then we have one more kind of magnets, which are electromagnets, which are also called temporary magnets. Okay, even we get uh, um, artificial magnets, I mean to say temporary magnets, which are not electromagnetic in nature. I'll discuss about all those things, but now this electromagnets part, we have touched them a bit, right? A current carrying conductor, external current, after supplying the external current, I mean the external potential difference, connecting that wire to a battery, that wire acquires magnetic property, right? When we switch off the circuit, then no current, no magnetic field, no magnetic effect. So they are all electromagnets. Okay, and first one, naturally occurring artificial electromagnets. Okay, and there are other classifications also, like temporary magnets. What are those temporary magnets? When we bring a piece of iron, like nail, in contact with a magnet, that nail also acquires magnetic property, isn't it? You can observe it. When you have a magnet, you just let me show that. Okay, just a minute. So this is the weight that I have from the weight set, which weighs 50 gram. Now, as you can see, this is a piece of iron, this is a piece of iron. There is no attraction between them, right? You can see it falls down. There is no attraction, right? So this is not a magnet, right? Yes, you are right. But if it attracts, then we call this a magnet. Okay. So now here is the bar magnet, which is a permanent magnet. And now once we make the magnet come in contact with the iron or this material, even this material has also acquired magnetic property now. Okay. You want to see that? See, now before this magnet was in contact with the weight, it was not magnetic in nature. But when this material has come in contact with the magnet, this material or this mm, uh, weight has also acquired magnetic property. So now you can see the effect of that magnetic property. Can you see that? See, this weight can only attract the key when this has magnetic property. So temporarily, this one, the weight has acquired magnetic property when, since it has come in contact with the bar magnet. Now if I leave the bar magnet, observe carefully, if I leave the bar magnet, then the magnetic property is lost and hence the key should fall down. Okay, right. So that's it. These are all temporary magnets. Okay, right. So this is about different types of magnet, history of magnet, and all, and definition of magnet. Okay, so there should be properties of magnets, right? Let us see few properties of magnets. As of board's syllabus is concerned, three properties has to be memorized. Okay, there are more than three now, but three of them must be memorized. They are very important. You should recall them. So one of the property is, let us begin with the basic property. A magnet can attract lighter particles of iron, cobalt, nickel, etc. Right? Next, this comes from the property of attraction, attractive property. Okay, this is called attractive property. Then we have directive property, right? So when it comes to directive property, we say a freely suspended magnet. Okay, a freely suspended magnet always comes to rest, or we can say always rests in north south direction. Always rests in north south direction. This is the directive property of the magnet. Next, moving ahead, we have few properties regarding poles of the magnet. First property, very important one, is a magnet has two poles. Okay, which are those? North pole and south pole. Okay, two poles, north pole and south pole, with same strength. Okay, or you can say with same magnetic strength, which means, see, this is north pole of the magnet. Okay, what the magnetic effect or magnetic strength, what is magnetic strength? Yeah, we'll go for the mathematical discussion later, but now I can give you the idea. Like, magnetic strength can be taken as the ability of the magnet to attract materials. Okay, that's how you can take it. If it can attract, if the force of attraction is too much, then we can say it has good strength. If the force of attraction is less, then we can say the magnetic strength is less. Both the poles of a magnet possess same magnetic strength. Okay, see, this can attract this pole, the north pole of this magnet can attract this one with the force which is equal or more than its weight, right? So this weight can only stick to the magnet when the force of attraction of the magnetic force, is more than the weight of the weight or weight of the this body. Okay, weight of the body. So now, even if I change the pole from north to south, you can see still it can attract the body with the same amount of force. That's why it is still sticking. If the magnetic strength is lesser, then it cannot hold this body. Okay, let me show you a small magnet with less magnetic strength, because we'll see what are the factors which will decide magnetic strength. Before that, I'll bring another magnet, the smaller one, which has less magnetic strength, and hence it cannot attract with the same amount of force as of this. Okay, just a minute, I'll bring it and show you now. Okay, see, this is another magnet where north pole and south poles are mentioned. Actually, this is north and this is south pole. See, this is a small magnet, okay. Yes, it does attract this lighter the other bodies, but the force of attraction is not sufficient enough, or it's not same as of the previous magnet. It has less magnetic strength. See, okay, observe this. No, right? Okay, look at this. It can somehow lift it. Yeah, okay, fine, but with little effort it will fall down. Okay, so making it stick to the magnet itself is difficult, but this one, you can see, this is of good strength and you can easily lift it and it will not fall because the magnetic strength is more. So now the point is, both the poles of a magnet, of the same magnet, possess same magnetic strength. Magnetic strength means the ability to attract, or the force of attraction which can be expected from a magnet. Okay, so that is one of the property uh, with regards to the poles. And now moving ahead, it's about the attraction. When we have two magnets itself, when we have two bar magnets, then like poles, okay, what is like poles? North pole, north pole, south pole, south pole, okay, they are like poles. Like poles of magnets, or like poles is enough. Like poles always, like poles of magnets, like poles of always, like poles of magnets always repel each other and unlike poles attract each other. Okay, so this is the next uh, point, or next property of the magnet, which is very easy and important at the same time. Next property with regards to magnets is, an isolated magnetic pole does not exist. An isolated magnetic pole does not exist. What is this isolated magnetic pole? Isolated magnetic pole is nothing but a single pole or monopole. Okay, see, when I say a magnet, north pole and south pole always exist together. Okay, when I say an electric dipole, there also similar to this we will have a positive pole and negative pole. They are charges, positive charges and negative charges. Here we have north pole, south pole. In the electric or electrostatics, in electrostatics we can actually separate this positive pole and negative pole, right? We can do it, but when we come to magnetism, we cannot separate a north pole and south pole. You can say, sir, what if I break it in the middle? If you break the magnet in the middle, then what happens is north pole stays in the same place. The half, the right part of this half will gain south pole. Okay, like this. Okay, say uh, after breaking this, say this is the magnet that we get, then the north pole will remain the north pole itself, but this part of the broken part, or this side of the broken part, will become south pole. So how many times you break a magnet, that doesn't matter. Both the poles of the magnet always exist with each other. Okay, let me take this point and discuss it detailedly now. Before I discuss that, I would like to give you one more property, okay, which I've just shown you. Okay, Materials which come in contact with the magnet also acquire magnetic property. Okay, that is the next property. Okay, let me rub and write. Then very easy property again, which I have just shown you. The next property is as follows. Okay, materials like iron, cobalt, okay, materials like iron, cobalt, nickel, when come in contact or come closer, okay, closer to a magnet, also exhibit magnetic property. This phenomena is called induced magnetism. Okay, induced magnetism. So if the question is what is induced magnetism, you can write this. Materials like iron, cobalt, nickel, when come in contact or closer to magnets, they also exhibit magnetic property, and this phenomenon is called induced magnetism. Okay, these are few properties of magnets, and now I'll just explain this property. An isolated magnetic pole does not exist. Okay, magnetic monopole does not exist. And let me give detailed idea about that now. Okay, these properties are very important. You need to just memorize or at least 3 properties out of it. Okay. Okay, so magnetic monopole does not exist. Okay, see, now say you have a magnet of this big size. So this is north pole and this is south pole. When we break this magnet exactly in the middle, then we have one piece here and the other piece here. These pieces will also have both the poles. So the first piece of the left side of the first piece will have north pole similarly, and this part, the broken part side, will have south pole, will gain or acquire south pole. This will remain south, but this will have north pole. Okay. Now you can ask me to break it again. Okay, but what happens to uh, the strength of the magnet? See, since we have broken exactly in the middle, strength of these two magnets will be half of the strength of this bigger magnet. Okay, keep that in mind. Strength of these magnets, small magnets, will be half of the strength of these two, the bigger magnet. Then I break it in the middle again, and once again the same phenomena continues. North will stay north, the opposite pole will be negative, I mean south. So here south, but this will become north, and similarly this will be north, this will be south, this will be north, this will be south. So this phenomena can be taken to any level. But now you can say, sir, what if I break it here, too much thin space, with too much in a thin slice. If I take out a thin slice out of it, say this much small slice, then even then this will be north pole, this will be south pole. You might say, sir, I'll break it again. Okay, fine, you break it again. Okay, fine, you break it again. Continue the process. What you'll be left with finally, think of it. You'll be finally left with an atom, isn't it? If you keep on breaking this, finally you'll be left with an atom, right? Now, what is an atom? Atom has got revolving electrons inside it. At the center there will be nucleus, which will also give us the magnetic effect, but let us not consider the magnetic effect due to the rotation of nucleus. We'll just stick to the revolution of electrons. when the electrons revolve, they produce magnetic field. And when we have unpaired electrons in the atom, the individual atom now can act as a magnet, isn't it? You just try to recall the magnetic field due to a circular current carrying coil. Can you recall that? So when we have such an arrangement using right hand thumb rule, this will be the north pole and this will be the south pole, like this, right? Clear on that? So very easy one. And now if a current carrying conductor can have two poles, similar to this, an electron revolving in its orbit will also have the same kind of property. This will be north, this will be south, right? So since an electron can have both north and south pole when it revolves, here we have unpaired electrons. When we have unpaired, one of the electron will be not paired, and hence you will have a net magnetic field present. When we have paired electrons, when we have all the electrons paired, then if one of the electron is moving in clockwise, the other will be moving in the anti-clockwise. So they cancel the magnetic effect, okay, when we have paired electrons. When we have unpaired electrons, there will be one extra electron which will have either clockwise or anti-clockwise revolution, which will produce net magnetic field in the entire atom. So a single atom, due to the revolution of that unpaired electron, will now have magnetic field. So that magnetic field is always north and south, right? Somewhat like this, north and south. That's it. That is why even if you break it into a single atom, that single atom will also have two poles, north and south, right? Because we have studied in the last chapter that a current carrying conductor will have two poles, north and south. Using right hand thumb rule, we can get the direction of north and the direction of south. That's it. Same logic can be applied to the atom, and you just try to build it up. Few atoms together becomes piece, and hence north south, piece of north pole, north south, and so many pieces of them becoming a magnet of good considerable strength. That itself is a bar magnet. Okay, so this is the detailed discussion of magnetic monopole, non-existence of magnetic monopole. Okay, that is why magnetic monopoles does not exist in nature. Okay, we have not yet discovered it. There is experiment happening on it, a lot of research is happening, but we have not yet seen magnetic monopoles. Thank you. We shall discuss more on magnetic field lines and take a derivation in the next session. Thank you.